Okay, so we're talking about probability, right? The first question says 160 people went into a coffee shop, right? So we observed 160 people. 60 of the people bought coffee and a donut, and the rest of them bought coffee or a donut. The question asks us to figure out what the probability of the next person coming in will buy coffee and a donut. Okay, so you said you set it up as a fraction. What did you say the fraction was?
160 over 60.
Okay, well, experimental is actually
60 over.
Yeah, total observed. And then depending on what it is, I can't remember what the actual definition is. But in our case, it'll be people who bought coffee and a donut. Okay? So what that means is how many people bought coffee and a donut?
60.
Yeah. And how many people were observed?
160.
Good. So in order to actually figure it out as a fraction, they'd probably want us to reduce this to lowest terms when we go to reduce this fraction. So if you look at this, how can we reduce this?
60 divided by 160.
Okay, that'll bring us right down to some decimal over 1. That'll put it into decimal form. But let's say I still want it as a fraction in lowest terms. We have to think of numbers that divide into each of these. Okay? Whenever you're doing probability, you try to break things into lowest terms. If you were to go to a casino or something, they wouldn't say your chances are 60 in 160. They'll break it down to the lowest fraction possible. So 60, if we look, see how there's a 0 at the end of both of these?
Yeah.
That means the number 10 definitely goes into both. So we can definitely divide by the number 10, both of these numbers, to get a lower fraction. Okay? So if you want to use a calculator, what would 60 divided by 10 be?
10. Wait, no, 6.
Yeah, that's right. I'm going to move this down here so we have some room when we do it. That's right. It'd be 6. And what would 160?
16.
Yeah. So now we're 6 over 16. Still the equivalent. Still the exact same thing. Just a little easier for us to wrap our heads around. Now, let's keep going. Both of these are even numbers. So if both are even numbers, do you know what goes into both of them?
2.
Yeah, that's right. So let's go again by 2.
2 and 8.
So in this one, 6 divided by 2?
3 and 8.
Yeah, 3 and 8. 3 is a prime number, okay? So we can't actually divide anything into it. So this will actually be our lowest term fraction here. So it's 3 and 8. So the probability of the next guy coming in would be 3 and 8 as a fraction. So as one person, that doesn't really give us a good idea. What it's saying is if 8 people come in, so if 8 people come in,
3 buy coffee and a donut?
Yeah, it's most likely that 3 will buy coffee and a donut. Coffee and donut. That's what it's saying. But we're talking about the next guy himself. So when we're doing something like that, we want to actually put this into a decimal or a percentage. So how do we turn this into a percentage or decimal? Do you know?
Decimal, 3 divided by 8.
Yeah, well, we do 3 divided by 8. That's right. So what are you going to get there?
0.375.
0.375. So right now we're in decimal form, which is good. So that's the next step. Oh, spelled that wrong.
And then it's a 37.5% chance.
Yeah, that's right. To turn the decimal into a percentage, we multiply by 100, which gives us a 37.5% chance that they buy coffee and a donut. Okay, so second question here, probability. We kind of point forward that this company's got some malfunctioning chips, and the company quickly tests 10 different chips from the production line, and they find that they all work. Okay, so what that means is even the lowest amount, they didn't even find 1, right? So 1 out of 10 would have gave us what percentage?
10.
10%, that's right. But what's happening here is if 2 of them didn't work, what would that percentage be?
20.
Yeah. What's happening here is they're jumping up by 10% at a time. So it's likely that less than 10%, because they are having malfunctioning chips, doesn't mean that they all are working. For sure, there seems to be something wrong because they're getting complaints. Now, as a big company, they might make millions or billions of chips, right? And they tested only 10. If we're going to do better quality control, we need to get to smaller numbers, right? So what would be a larger number, something that'd be better to look at in this case?
3 and 10? Or 4 and 10?
Well, 4 and 10 would be talking about how many are working or not working. What we're talking about is the amount of chips they actually tested. And they tested 10 chips. That's text, not tested. They tested 10 chips, right?
Yeah.
If we wanted to get to lower percentage increases, so like if 1 wasn't working, it would have been 10. If 2 weren't working, it would have been 20. But see how that drops? In this case, none of them were not working. So that's essentially 0%. But what I want you to recognize here is that we're jumping by 10% at a time. It's a pretty big jump, right? It probably means that less than 10% of the chips aren't working. Again, but because there is malfunctioning chips, some are probably not working. So we need to break these percentages down even more. And what that means is we need to test more than 10 chips. Okay? What would be a round number that they tend to use for testing chips? Or testing anything, really? If a company produces millions, what would be a bigger number we could look into?
40.
Yeah, we could look into 40, right? And let's talk about how that percentage would change. So let's say we talked about 1 in 40 and then 2 in 40. Right? 40 is a bigger number, so that's definitely going to improve our quality control. So we'll call this A. This will be our B. As a percentage, what would 1 in 40 be as a percentage? Can you bring it up on the calculator?
2.5%.
Okay. So that would be 2.5. So if one of them wasn't working, that means 2.5% wouldn't be working. What if 2 of them weren't working?
5%.
Yeah, that's right. Jumps right up to 5%. So it's increasing by 2.5 every time. Okay, but what if we're talking about a company that it's less than likely that 2.5% isn't working? Let's say it's an even smaller fraction. How can we increase this quality?
60.
60. What would another be a big round number that's really easy to get percentages out of?
50.
50 is easy to get percentages out of, but it's only a small increase from here, right? So if we did 1 in 50, you're right, 50 is going to be 2% each time. So it's going to go up by 2%, and then 4% would be 2 in 50. Now, if we're a company that produces millions of chips a year, right? We probably want to know right down to the percent of what our malfunctioning chips are going to be. So this was our C. So what number in the denominator here would give us a 1% increase each time? If 50 gives us 2%,
80. Wait, no, 70.
70. Let's try 70. 1 in 70, 2 in 70. What does that give us as percentages?
1.4.
1.4. And then what would 2 give us?
2.8.
2.8. Are we going up by only 1% each time? No. So we've got to find a bigger number.
So 90%.
Let's try 90. 1 in 90 and 2 in 90. What kind of percentages do those give us?
1.1%.
1.1. And what would the next one be?
2.2.
2. Yeah. So still not by a percent. What would be another number to try?
Um, 93.
Okay, let's jump even higher.
No, 93 gets you to 1%.
It still gives us 1.01 or 0.7, right? Let's jump even higher.
95.
What would 1 out of 100 be as a percent?
1%.
It would give you exactly 1%. And what would 2 out of 100 be?
2%.
2%. So if we were to use, and remember the bottom number is talking about number of chips tested, right? We were talking about first testing 40 chips, then 50, then we jump to 70, 90. If we test 100 chips, for each chip that's wrong or malfunctioning, that's the exact percentage that's going to be missing. All percentages are done out of 100, okay? So it's important to know that, right? Everything's done out of 100 in terms of percentage. So if 2 chips malfunctioned out of 100, that would be 2% of our product is malfunctioning, is what that would mean. Now, we wouldn't have been able to find that if we only tested 10 chips, because it seems to move up by 10% at a time, right?
Yeah.
If we tested 50 chips, we might have found 1 in 50 chips. If, like I said, if 2 of them malfunction, we would have found 1 in 50 chips not to work. But 100's a great number. If we find 0 out of 100, it still doesn't mean 0%. We could test even higher. But what it does mean is less than 1% of the chips aren't working. Okay? So let's say they found 0 out of 100. Okay? It doesn't mean we don't have malfunctioning chips. It just means that the highest probability, which is 1 of 100, and which equals 1%, we have less than 1% of the chips not working, which is a pretty good percentage of the company. Yeah, so say we did something like 700. Now, the problem with that is if you're a company who's producing maybe millions, right, and you're testing 700 chips maybe a month or a day, that's a lot of product that you can't sell. So you don't want to go too high. It depends. It's almost like a ratio of how much we produce. If we only produce 1,000 chips, we're not going to test 700 of them. That's only going to leave us with 300 to sell, right? That's where like a 1 in 10 might not be a bad idea.
Wouldn't you be able to sell them after you test them?
I'm assuming the tested ones have to have already been put into a computer and tried out, so then they'd, I think, technically have to be considered refurbished as a company. And we don't want to test all of them because that's going to slow down how fast we produce things. Yeah, it's going to slow down our production. So what we're going to do is, if we're a company who produces millions, 100 is not a big number to do. The 100 is fine. If you only produce 150 a year, well then 100 is a lot, right? It really depends on the company and how much they produce. So how could a company do better for quality control? Just by testing more chips. That's essentially what we get at. 100, like I said, is a good number because for each one that's wrong, we know exactly what percent it probably is. And it could be like 1.5%, but then you get into testing 1,000 chips. And the only time you really start to do stuff like that is if you're producing maybe millions of something a year. Okay? Does this mean the chips are all likely working? No, we talked about that. Okay, good. Okay, so the next question is decks of cards. They've given us a deck of cards. There's 52 in the deck, and they said there's 2 jokers. So that means there's actually 54 cards in the entire deck, which is very important because for all of our probability, we're probably going to be going out of 54. They wanted to know how many of the cards were red, right? And you knew that there are 4 different suits, right? We had 4 suits. What are the suits? We have
clubs.
Yeah. And then
Spades.
is the other.
Hearts and diamonds.
Hearts and diamonds. And diamonds. DIAMO. I think that's right. Yeah, hearts and diamonds. Okay. Now that's of the original 52, right? The jokers don't count in those. The jokers don't really fall into any of those 4 suits. So you knew that 13, because it's broken into 4, we take that 52 and we divided it by 13. Oh, sorry, we divided it by 4, and we found out there are 13 cards that are clubs, 13 that are spades, 13 that are hearts, and 13 that are diamonds. Now, this question asks us how many red cards there were. Well, since hearts and diamonds, there's 13 of each, that means there'd be 26 out of the total of 54. So what did you get as a percentage when you divided those?
24.07%.
24.07%, which they'd probably say is approximately 24%. Okay? Depends on how far your teacher wants you to round the number. So that's good. We'd say that if you were just reaching into a random deck, you have a roughly 24% chance of pulling out a red card. A black face card. So let's talk about that. Face cards. What are the face cards?
King, queen, and jack.
Yeah, so we get a king, queen, and jack. Okay. Now, technically, how many kings are there altogether?
12.
12 kings?
Oh, no, 4.
4. That's right. There's 4 kings. How many queens?
4.
And how many jacks?
4. I was thinking all of them together.
Yeah, okay, that's good. You're right. There's 12 face cards altogether. Now, that's a king for each of the diamonds, hearts, clubs and spades. Because we're talking about only black, how many black kings are there?
2.
Yeah, there's only 2. How many black queens?
2.
And how many
2.
black jacks? Good. So how many black face cards are there?
6.
That's right, we add those together. There are 6 black face cards. Now, a face card. Jokers, I don't think we consider face cards, okay? So we're going to assume, again, it's a... How many cards are in this actual deck?
52.
Just 52? Are the jokers not included anymore?
4.
Yeah.
54.
Yeah, we have 54. And how many of them can be black face cards?
6.
6. So what is the percentage or likeliness of you pulling out a black face card?
11% chance.
11.1%. So approximately a 11% chance of pulling out a black face card. It's not great. It's 1 in 10, right? So if you were to try 10 times, you'd probably get it about once. Let's go into the third one, ABC. What's C asking us?
An ace, 2 or 3.
Ace, 2, or 3, okay?
That would be 12 cards again.
Yeah, you're right, because there's 4 of each. We already know that. An ace has 4. A 2 has 4. I should write it as a word. So what is the percentage going to be as I'm writing these down then?
11.1.
Is it going to be 11.1? 2 or 3. We know there's 4 of each, which gives us 12 when we add it all up. What's the fraction going to say?
No, it's going to be 21.2.
You're going to double it. Very good. We're going to double it. So we have 12 in a 54 chance. We knew 6 was 11%. We were looking at about 22.2% chance of pulling out an ace, a 2, or 3. Okay?
The red card that is not a face card.
Ah, okay.
So, 20 out of 54.
How did you know it was 20?
Because there's 2 diamonds, 2 jacks, and 2.
Okay, so you knew that there was how many face cards that are red?
6.
Yeah, you knew there were 6 face cards that are red. And how many red cards were there altogether?
26.
There are 26. And we want a face card that's... Sorry, we want a red card that's not face. How did you figure out 20 from those two numbers? 26 and 6?
Face cards.
That's right. So you took away the 26 and you subtracted your 6, which gives you 20 out of 54. What's the percentage of pulling out a red card?
37.03.
37.03% likelihood of getting one of those cards. There you go. Very good. Okay, fourth question talks about probability of dice. Right? And they're asking us a whole different bunch, but we actually have to find the theoretical probability of how many options there are in dice. Right? So one of the things you did is we start at the numbers. How many options for 0 if you roll 2 dice?
0.
No, yeah, definitely not going to happen. Right? We have 0 options for here. What about the number 1?
0.
Yeah, won't work. We don't have options of 0 on dice. So neither of these, 0 chance, 0 chance. This can't happen. The number 2. What can we roll on each dice?
1.
A 1 and a 1.
Isn't there 24 options?
We're going to find out right now if there's 24 options. What about for the number 3?
2 options.
And what are the 2 options?
1 and 3 and 2, 3 and 1.
That will give us 4 for each.
Oh, 2 and 1 and 1 and 2.
Yeah, that's right. So we have those 2 there. So that kind of encompasses the 3. So there's actually 2 options for the number 3. Because we roll the exact same thing, but because there's 2 different dice, I could roll a 2 on this dice or a 1 on this dice. Or on our red dice, I could roll a 1 and a 2. So we actually have a 2. 2 different chances or 2 different ways of getting the number 3. Let's talk about the number 4 now. Now the number 4, I can roll a what?
2 and a 2, 1 and a 3, or 3 and a 1.
I have a 2 and a 2, a 1 and a 3, and a 3 and a 1. So how many chances does that give us, or how many options?
6. I mean 3.
3. We have 3 different options for that one there.
For 4, you have...
For 5?
I mean for 5 you have 4.
Okay, what are they? 1 and...
1 and 4, 4 and 1, 2 and 2, and
2 and 2
3.
will work.
I mean 2 and 3.
Yeah, and then...
And then 3 and 2.
That's right. The reverse. So what we're going to do from here on in is, because we know the reverse is always going to be an option, so there's 4 options here. I'm just going to add what we're going to say for the next one, like when we do the number 6 here. Number 6, we have 1 and 5. I'm going to say or 5 and 6. So I'm going to say there's two options of 1 and 5. That's how I'm going to represent it, okay? Just so we don't take up a whole page when we do this.
Okay.
So we have 1 and 5. What else do we have?
3 and 3.
3 and 3. Now, how many options of 3 and 3 do we have?
2.
Do we? Can I roll 3 two different ways on one dice?
No.
No, I can only do it once. So that's actually a special case. When you get double numbers, just like our up here when we looked at the number 4,
Yeah.
we could only do 2 and 2 once, but we could do 3 and 1 twice. Okay? So that's one of the rare ones. What other options are there? 1 and 5, 3 and 3. What about the number 2?
2 and 4.
2 and 4. How many times can we roll that?
2 twice.
Yeah, we can roll that twice. Right? So options for the number 6, there's actually...
3.
Well, we're going to add those up, right?
6. 8.
Let's count
5.
these numbers.
5.
2 plus 1 plus 2, which gives us our 5. Right? The number 7.
6.
Let's see. Okay, number 7. What are the options?
1 right now. 1 and 6.
Yeah, 1 and 6. How many options of that?
2.
2 different ways of doing that. What about the number 2?
5 and 2.
Yeah, how many ways of doing that?
Twice.
And
3 and 4.
3 and 4. How many ways of doing that?
2.
So how many altogether?
7. 6.
6. 6 different ways of doing it. Let's look at the number 8 now. How many ways can we get the number 8?
7.
1 and 7 gives us
8.
how many different
Two.
ways? 2 ways of doing it. 2 and...
6.
Now here's a question. On a dice, if we're jumping ahead,
How likely is it to get a 6?
so how likely is it to get a 7? That's what I want to know. What's the likelihood of getting a 7 on one die?
Very unlikely.
Why is it very unlikely?
Because you can't roll a 7.
So you can't, so it's impossible. You can't actually roll a 7. So that's no good. There
Well,
isn't 2 chances of getting it here. Now there is a possibility of getting a 1 and a 6, and a 2 and a 5, and a 3 and a 4, which would differ than the number 7. I can roll a 1. I can't roll a 7. Impossible. So this is actually doesn't make sense. I can't get that option. Okay, so that's actually not an option here. Because dice only go up to 6.
Unless you get one of those weird dice.
We're assuming we're using a six-sided dice. Okay, so 1 and 7 doesn't work. What does work?
2
And
6.
yeah, and there's 2 different ways of doing that. What else?
4 and 4.
Okay, 4 and 4. There's how many ways of doing that one?
1.
1. And what other number?
3 and 5.
3 and 5. How many ways of doing that?
2.
Any other ways? No. So how many options are there? 2,
5.
5. So
Oh, so it's going down.
it's going down again. So let's look at the entire page quickly. Okay. We can kind of estimate what our numbers are going to be. With the number 2, there's 1 option. For number 3, there's 2 options. Number 4, there's 3. 5, there's 4 options. 6, there's 5. And 7, there's 6.
5.
8, there's 5. So instead of writing out all the options again, I'm going to jump down.
Go back down.
It's going to go back down exactly.
Because 7 is the highest.
Because yeah, you're right. 7 has the highest probability of getting rolled in dice. That's why in certain games 7 is quite a special number. So 9. If there's 5 options for the number 8, how many options for the number 9?
4.
That's right. For the number 10?
3.
For number 11?
2.
And for the number 12? What's the only option?
6 and 6.
6 and 6. So let's look at the whole page again. A whole bunch of numbers here. Let's highlight what we got. 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. How many different ways can I roll dice?
124.
Well, let's add these up. I think that's a pretty high number.
Alright, no, 24.
Let's see. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 15, 21, 27, 34, plus 3 more, 37. Is that what I'm counting here? Let's add them. Make sure it's got the number 1 plus 2 ways plus 4 plus 5 plus 6 plus
5.
36. 36. So what they're telling us is there are 36 ways to roll dice. That's quite a few options. So that's a theoretical probability. Now, once we have that number, and there's a way we could have discovered this.
12 times 3.
12 times 3, but let's talk about the dice themselves. How many sides are on a dice?
6.
6 on each of them, right? So if there's 6 sides.
6 times 6.
Yeah, and 6 sides. If we had multiplied those two numbers, we would have got our 36. But I just want to show you all the different options there. Okay. So let's jump to a new page. What's the first question to ask us?
No.
We know everything's out of 36 now. First question says what?
So, right, 2 dice are rolled. Find the probability that the sum of the number is 11.
11. Okay, so let's look down to our number 11.
It's 2.
There's 2. 2 out of what?
36.
So 2 out of 36. What's the percentage chance?
$5.5.
5.5% chance that you're going to roll an 11. It's pretty low. What's our next option here? B.
Non-11.
Not 11. Okay, so there's 36 chances. How many chances of not getting 11 does that mean?
94.5.
Yeah, you're right. You subtracted the 2, right? Tell me how many options there are. If 2 of the options...
34.
Yeah, that's right. It'd be the same as writing 34 divided by 36, which gives us our 94.5% chance of not rolling 11. So not number 11 on dice. Okay, what about C? Rolling a 2, a 3, or 4. What does that mean we have to add up?
6.
We got to add up our options for the number 2, number 3, and number 4. And you're right, that gives us a 6 out of 36.
16.6% chance.
Okay, so we get a 16.6% chance of numbers 2, 3, and 4. What about D?
A multiple of 3.
A multiple of 3. What are multiples of 3? So numbers that are multiples of 3?
3, 6, 9, and 12.
3, 6, 9, and 12. So we know it's going to be out of 36. This is how we figure out what are the options of rolling 3? We have 2 chances. What about a 6? We have how many?
5.
5. What about a 9? Scroll down. Chance of rolling a 9?
4.
And chance of rolling a 12?
1.
Okay, so what does this say? 2 plus 5 is 7. Plus 4 is 11.
12.
12 and 36. So what's our percentage?
33.
33% chance of rolling a multiple of 3. That's all right. E. Greater than 1. Can you roll a 1? No.
So it's a 100% chance.
100% chance. All of your rolls have to be greater than 1. You can't roll a 1 in dice.
Greater than 3.
Greater than 3. Okay, so let's talk about this one. It's actually kind of a bit easier to say, well...
Take away 1 and 2.
Yeah, take away... Well, 1 we know is 0.
2 and 3. So
1, 2, and 3. So that would be a total of 36. Subtract. What are the chances of getting a 1? Sorry, a 2?
So take away 3.
Yeah, we take away the number 3 out of 36, which is going to give us
80.3. Wait, yeah, 83.
Oh, 83 or 80.3?
I don't know, but 3 divided by 36 times 100 is 8.3.
Oh, you did 3 divided by it. What about 33 divided by 36? That gives us a times 100. What are you going to get?
91.6.
Yeah, 91.6% chance of rolling something greater than a 3. Okay?